The next thing we will come to find out as it pertains to systems is that much of the theory of systems of n-linear first-order differential equations is very similar to that of linear nth-order differential equations in general. For example, we can also define a system initial value problem. Let's let t sub 0 denote a number in an interval I, where all of the component functions x1 through xn are continuous and differentiable. Then we'll denote the initial vector x of t0 is simply the vector formed by evaluating each of our xi's at the value t equals 2 to t naught. Okay. And in which case our linear system will now look like this in matrix format. An initial value problem on a given interval will be of the form x prime equals a times x plus f, where again, kind of remembering that explicitly, recall that a of t and f of t, these are both functions of t, even though they're matrices. And then this is going to be subject to the initial condition that our solution matrix, our solution vector x evaluated at t0 should be equal to x naught. And that x naught is simply the value we would get when we evaluate each of these component functions at some particular value of t. So we also have initial value problems for systems. And we now come to theorem 8.11, which discusses when we can expect a system to have a solution. And in particular, this is the existence of a unique solution. Let's let the entries of the matrices a of t and f of t be continuous functions on some common interval I that contain the point t0. Then there exists a unique solution of the initial value problem on the interval. So as long as our functions are continuous, a and f are continuous on a common interval I, where t naught is a point in I, then the system will have a solution on that interval. Much like what we saw when we started with first-order linear differential equations, we will also focus highly initially on homogeneous systems, and that's where that f of t matrix would be identically equal to the 0 matrix. So in the next several definitions, we're going to be concerned with only homogeneous systems. So we're going to assume that the component functions ai, j are going to be continuous functions on t, and the f functions themselves would be all 0. Because they're going to be the 0 matrix right now, because we're talking about homogeneous systems. But the 0 function is continuous as well. One of the results we recall previously was the superposition principle, and that also holds true for systems. Suppose we have a set of solution vectors x1, x2, up to xk. Remember, each one of these is a column vector that satisfies the differential equation system. Then it's also true that the linear combination of those will also be a solution. So suppose that these are solutions on the interval I, then their linear combination, where ci are just some arbitrary constants, will also solve the system. Okay. Let's take a look at the superposition principle in example 3. I'm not actually going to show that the linear sum of these two is a solution, but let's at least verify that x1 and x2 are two solutions to the differential system x prime equals this matrix A times x, where x will be the given functions x1 and x2. I'll start by checking x2 first, because it's definitely a significant less amount of writing. x2 is the column vector 0, e to the t 0. We need x prime of 2, which coincidentally works out to be itself. We differentiate each entry term by term. The derivative of 0 is 0, the derivative of e to the t is e to the t, and the derivative of 0 is 0. We now are going to plug that into the system. We want to see, is it the case that x2 prime times a is equal to x2? So let me just kind of work this out. We have our 3x3 matrix A, which is 1, 0, 1, 1, 1, 0, negative 2, 0, negative 1. And we're going to multiply that by x2, which is 0, e to the t 0. And we want to see, does that equal out to x2 prime? So to start, this is a 3x3 matrix times our 3x1 matrix. So we begin by taking the first column, it's going to be the first row times the first column. So it's going to be 1 times 0 plus 0 times e to the t plus 1 times 0. That was our first row times our first column, produces the first row of our solution matrix. We're now going to take the second row times this column. That's going to give us 1 times 0 plus, now we have 1 times e to the t plus 0 times 0. And now lastly, we're going to take the third row times that column vector. That will produce negative 2 times 0 plus 0 times e to the t, and then plus negative 1 times 0. Typically, I wouldn't write out all of this, but it might have been a while since some of you have maybe worked with matrix multiplication. So I'm trying to show as much details as possible, so maybe it'll help as a good refresher. But when we simplify this is going to be 0 plus 0 plus 0. So the first row is 0. Then we get 0 plus e to the t plus 0. That is e to the t. And then this is 0 plus 0 plus 0, which is also 0. And sure enough, that is equal to x prime, x2 prime. So that shows that this vector is a solution to the system. Let's now go through and show that x1 is also a solution as well. Again, just like with any other object and being a solution, you need to plug it in and see if it makes a true statement. So we now want to check, is it the case that x1 prime, is that equal to a times x? We have x1 here, so I'm not going to recopy it down, but we do need the derivative of this. So we're going to differentiate component by component. The derivative of the cosine of t is going to be negative sine t. The derivative of negative 1/2 cosine t plus 1/2 sine t is going to be a positive 1/2 sine t plus 1/2 cosine t. And then the derivative of the third row, that's going to be a positive sine t minus cosine t. So this is what, presumably, this is what a times x should be equal to. Let's go ahead and multiply that out. Here's our matrix A. So we're going to take 1, 0, 1, 1, 1, 0 times negative 2, 0, negative 1 times x1, which is cosine t negative 1/2 cosine t plus 1/2 sine t minus cosine t minus sine t. So let's see what that's going to be equal to. And this time I might write a little bit less since we're going to need a lot of room. We're going to begin, though, by taking the first row times our column vector. And I'll, just for illustration, maybe I'll write that in orange. We take the first row times the first column entry. 1 times cosine t is cosine t, plus 0 times that entire second row will produce 0. And now we have 1 plus 1 times that third row. 1 times negative cosine t, negative sine t, is simply going to give us a negative cosine t, negative sine t. Let's make a little more room here. Let's now go ahead, we're going to take the second row times our column vector. We have 1 times cosine t, so we're going to get a cosine t here. We now have a 1 times this middle row. That's going to produce a negative 1/2 cosine t plus 1/2 sine t, and then 0 times the last one is going to be 0. We're now down to our third row. So let's multiply this row by that column vector. Negative 2 times cosine t is going to give us a negative 2 cosine t. 0 times the middle here, so second row times the second column, times the second row would give us a 0. So say, sorry, second column times the second row produces 0. And then the third column times the third row, negative 1 times the negative cosine negative sine t. Be very careful. Don't forget that when you're multiplying that to that quantity, it needs to be distributed. So that's going to ultimately produce a plus cosine t plus sine t. And now that we've multiplied it all the way out, let's go ahead and simplify what we can. These cosines cancel, so we're left with negative sine t. Here, a cosine t minus 1/2 cosine t will give us a positive 1/2 cosine t plus 1/2 sine t. And then down here, we have a sine of t. Negative 2 cosine t plus cosine t will give us a negative cosine t. And sure enough, if we check it, this is indeed equal to x1 prime. So that also shows that x1 is a solution to this system. And so we could ask, what is kind of the big takeaway from this? Well, other than, getting some practice verifying solutions to systems, what we can now say and what we can now claim via the superposition is the following. That it's also true that c1x1 plus c2x2 for any constant c1 and c2 in the real numbers is also going to be a solution to the system. So the following linear combination, we can write it c1 times cosine t negative 1/2 cosine t plus 1/2 sine t negative cosine t minus sine t plus c2 times 0 e to the t 0. That linear combination would also be a solution to this system. The next thing we're going to discuss is linear dependence and linear independence. So much like what we'd already seen previously with a single linear differential equation, let's suppose that we have x1, x2 up to xk be solutions of the homogeneous system in this case on some interval I. We say that the set is linearly dependent on the interval I if there exists constants c1 up through ck, not all 0, such that c1x1 plus c2x2 plus ckxk, in other words, such that linear combination would actually be equal to the 0 vector. Okay? And then if the only solution to this equation would be c1 equals c2 equals ck equals to 0, then that would mean that the solutions would be linearly independent. So if you can find not all values c equal to 0, such that this equation equal to 0, then the solutions are linearly dependent. But if this equation implies that c1 up to ck are all equal to 0, then that would mean that those solutions are linearly independent. Okay? And just like what we saw from before, the Wronskian can be used to determine whether a system is going to be linearly independent. And so this is theorem 8.13. Let's suppose we have x1, x2, xn. We assume that these are all solutions to our linear system. The Wronskian, so these solutions will be linearly independent on the interval I if and only if the Wronskian is non-zero. And to form the Wronskian of those solutions, it's going to be the determinant of the vector, the determinant of the matrix, such that the first solution vector would be the first column, x2 is the second column of this matrix, up to the xn solution vector, which would be the nth column of this vector. So just as we saw from before, if the Wronskian is non-zero, then these solutions would be linearly independent. If the Wronskian is equal to 0 for some value t on the interval I, then the solutions would be linearly dependent. Let's take a look at the next one. Let's take a look at example 4. In example 4, let's suppose that we have that x1, which was equal to 1, negative 1, e to the negative 2t, and x2, which is 3, 5, e to the 6t. We had showed in example 2 that these were solutions to some differential equation earlier. Let's also check now that x1 and x2 are linearly independent. So show that x1 and x2 are linearly independent. And this is going to be actually on the entire real numbers. Okay. So to do this, let's calculate the Wronskian of x1, x2. This is going to be equal to, remember, x1 should be the first column, x2 should be the second column. x1 is going to be e to the negative 2t, negative e to the negative 2t. Our x2 is going to be the second column. That's going to be 3 e to the 6t, and then 5e to the 6t. And then recall, if you're finding a 2 by 2 determinant, you take and you subtract the two diagonals. So you take the major diagonal a times d, you subtract the minor diagonal b times c. So this is going to be e to the negative 2t times 5e to the 6t minus 3 e to the 6t, this diagonal here, times negative 2e to the negative 2t. We can simplify this. We get 5e to the multiplication by like bases. You're going to add those exponents. That's 4t plus 6e to the 4t so we get that, and then we can kind of go ahead and combine those. So this would give us 11e to the 4t. We know that this is not going to be equal to 0, so if you set 11e to the 4t equal to 0, you would divide by 11, and we would get e to the 4t equal to 0. We know that e is never equal to 0, and because the Wronskian of x1, x2 is not equal to 0, that implies that x1 and x2 are linearly independent. And I got another 2. I'm not sure where that 2 is coming from, but there wasn't a 2 here. So this should be a negative factor. This will actually end up being a 3. And so it should have been an 8. My apologies. So it doesn't change the logic, but we always want to be as accurate as possible. We don't want to make any silly mistakes here, in case it actually could end up changing the results. But either way you slice it, e to the 4t is never equal to 0. Therefore, this Wronskian is non-zero, and our two solutions, x1, x2, would be linearly independent.